So hello everybody. Today again we are going to discuss the next lecture for the fluid mechanics. So this is I guess lecture number 5 as far as I have remembered. So I have written it as lecture 5. If it is wrong I will correct it in the next video. Okay. So it doesn't matter to us. Okay. So now in the previous lecture we have studied about state relations for liquid and gases, and we have came up to that like for gases we are having some state relations, but for liquids there is no such predefined or a perfect state relation for liquid. So that's all. And today lecture is very important as many questions in the college exams, ESE or GATE, both all of these they are having questions from this topic. Okay. And now for our basic understandings, the properties that we have discussed till now, prior to this lecture, that those lectures are known as primary properties. Okay. And the properties that going to discuss today and the upcoming lecture, that are known as secondary properties. Okay. So from this lecture we are going to discuss about secondary properties. Okay. So the most important secondary properties scheme is viscosity. Okay. Viscosity. Okay. So what's mean by viscosity? Okay. So viscosity means like how the fluid are uh, sticking to each other. Like for example, if you see honey, if you put it in the table it will get stuck there very tightly, but when you put water on any table, on any utensils, you will see that water flow very easily, and it can if you just shake your utensils the water can pour out. But in case of honey it will get stuck there only. Okay. So we can say that the honey is more viscous. Okay. So that stickiness of a fluid is in technical term we call it as a viscous. Okay. And there are some method that we have to study about viscosity in much more detail. Okay. So in technical term we can say that what is viscosity means. The viscosity relates for particular definition. So it for the definition, the technical definition, the actual definition of viscosity is it is a quantitative measure of fluid's resistance to flow. Okay. See, we have taken the example of honey and the water. Okay. So for example, if honey, you have put honey here, then it will get accumulated over the surface and it will not flow that much easily, even if you turn the even you turn this utensils like this, this would come like this, but the length of this fluid is almost even same. But in case of water the whole fluid came out from these utensils. Okay. So and this is the fluid resistance to flow. That means this honey having more resistance to flow and the water having less resistance to flow. Okay. So this is the the best method, best definition to think about it, like how the resistance occurring whenever a fluid is flow, then that is known as viscosity. Okay. So what viscosity does, so it relates the local stresses in a moving fluid to the strain rate. I'm coming to strain rate and all other things of the fluid elements. Okay. Of the fluid elements, obviously we are studying fluid, so that it should be fluid elements, not solid elements. Okay. So the fluid elements. Okay. Okay. Now so according to this definition, that means local stress we can denote it as a T, and the strain rate we say it as d theta by, in a particular we write it as a del theta divided by del T. Okay. Strain rate. Okay. So we can say that from this definition we can say that this tau is directly proportional to del theta by del T. Okay. So this represents local stress and this represents strain rate. Okay. Delta theta means change in length or change in angle. So this represent your strain. Okay. And when you divide it by time it will become a strain rate. That means delta theta dot. Okay. So this is that. And I'm drawing the diagram and you will get to know how delta theta is denoted here. Okay, so for example, let's say this is any fluid element. Okay, I'm drawing it very large, but it is actually in microscopic level. Okay, so don't get confused that the fluid element is too large. No, the continuum element of the fluid is too small. Okay, I'm just okay. Now we are taking a fluid element sheared in one plane by a single stress tau. Okay, and the shear angle, that means this one, that is del theta, will continuously grow with time as long as the stress tau is maintained. Okay, so stress is maintained as from here tau is, and we know it, it is directly proportional to strain rate. Okay, so we will write it like that. Okay, and this delta theta will keep increasing as tau gets increasing. We can infer this from this relation as well. Okay, and the up I mean how this condition is occurring. Okay, so this condition is occurring like there is one plate there and fluid is moving, and the upper part is moving with del u larger velocity. Okay, that means if this one is moving as a u velocity, the upper part is moving with u plus del u. Okay, okay, so how much this extra distance that would be covered is del u into del t. Okay, so del u is the velocity and del t is time. So for the distance that extra that upper fluid have been covered is del u into del t. Okay, so this is the extra distance that upper part is having covered. Okay, so this is also del t, and that the y distance we will take as del y. Okay, okay, so this relation is valid for many common fluids like water, oil, and air. So it shows linear relation. That's why we have written here. And this relation is this statement is also valid for all the fluid. But this linear relation means tau is directly proportional to only the single shear restraint, directly proportional to shear restraint. So this is only valid for normal fluids that we are using nowadays. Okay, in our life, like water, oil, and air. Okay, right. Okay, so these things are valid. Okay, and these things which are varying is known as Newtonian fluids. Okay, Newtonian fluids. Okay, so this name come from NIAN. Okay, Newtonian fluid. Okay, so this this, or we can say it as some people call it as a linear fluid as well. Okay, so because it following linear relations between a strain rate and the stress, so that's why some people term it as a linear fluid. Okay, so this name was this name has been done after the Sir Isaac Newton, who has first postulated these things according to resistance law, like fluid is flowing and some resistance is occurring. That I have told you initially in the definition itself. Okay, that some fluid having I mean they feel more resistance during their flow, and some fluid face less resistance during flows. Okay, according to that, the Newton having given some theory resistance laws. So the fluid that following this linear relationships, or that following the Newtonian's resistance law, those fluids are known as Newtonian fluid or the linear fluid. Okay, now from geometry, okay, from this figure, we can say that tan del t equal to del u into del t divided by del y, right? I mean this one is height and this one is base. Okay, so from this triangle we can say that height by base. Now I already say you, right, this fluid element is too small. Okay, too small means what? This delta t angle will also be very small, right? Very small, infinitely small. Okay, so we are taking means we are making this fluid as a continuum fluid, like one continuum packet of fluid. So that's why we are taking as a very small. So at very small values of delta theta, we can say that tan delta theta is equal to can be approximated as delta theta. Okay, so we can write it as delta theta equal to del u into del t by del y, and it can be written as del theta divided by del t is equal to del u by del y. Okay, So this is another relation that we find out from the geometry. This is from the definition, this is from the here. Okay, so two equations we have been found out. Okay, now we have seen above that ki tau is proportional to del theta by del t. Okay, so one constant proportionality must have to come to make it like a equation. Okay, like you have studied in your school days, your universal gravitational constant or any other thing. So we will write it as a tau is directly proportional to we will include here mu into del theta by del t. Okay, and it is also equal to mu into del u by del y. Okay, from this equation, okay, from 2 we can write it as like that. Okay, now the here one proportionality constant term has came, and that is mu. Okay, so what's this mu is? Mu is known as viscosity coefficient. Okay, viscosity coefficient. Okay, and it's since this equation is dimensionally consistent, so therefore mu having some dimension, right? And the dimension of mu is aft divided by l square. Okay, that means the stretch time. Okay, or am divided by lt. Okay, so this is the dimension of the mu. Okay, or the SI unit is kilogram per meter second. Okay, okay, and now okay, so we have learned in about viscosity coefficient. Okay, mu. So for mu, it is the viscosity of Newtonian fluids. Like in this case, the linear fluid which we are discussing here is it true thermodynamical properties that varies with temperature and the pressure. Okay, so generally speaking, the viscosity of a fluid increases only weakly with pressure. Okay, like for example, if we increase pressure from 1 to 50 atm, I mean if you increase the pressure 50 times, your viscosity only increases by 10%. Okay, 10%. So not significant changes seen by varying the pressure, but in case of temperature, the temperature having high strong effect on viscosity. Okay, so how this varies? Okay, so we will write it here. Variations of viscosity with temperature. Okay, and if we increase the temperature, okay, temperature increased, viscosity can both increase and decrease. Okay, so if viscosity get decreased or viscosity can increased. Okay, so if viscosity get decreased in case of fluid, okay, I mean liquid, and it gets increased in case of gaseous. Okay, so on increasing temperature, the viscosity of gases will get increased, but in case of liquid it get decreased. Okay, and so this temperature variation for it is valid for common fluids. Okay, that we are using in our daily life, like water, oil, or air, anything. Okay, and okay, so one more thing, just I will introduce it here. We will discuss it this one as in more detail in our upcoming lecture. Okay, so just pay attention, little attention here. So see, if we want to, like, you may ask the question to me. Okay, so like why we have this designed this part like del u by dy. Okay, why we are not dealing with this part of only del theta by del t. Okay, so the answer lies here is, so the shear stress is proportional to slope of the velocity profile, and it is greatest at the ball. That means if we are going to plot the velocity profile for a flow over a plate, like see, this is the plate and some flow is flowing from this direction. Okay, so Due to no slip condition, I mean no slip condition means like the shear stress here will be maximum. Okay, that means the velocity gradient del u by dl y is maximum at the wall. Okay, that means stress will be maximum, right? So the almost the this wall and this the fluid, the consecutive fluid, that means the fluid that is just touching the wall, that are having the maximum stress. That means this will follow the no slip condition. That means the fluid which are just consecutive to the wall are having zero velocity. I mean this fluid part element which are just near to the wall is having zero velocity. That's why this is a velocity profile, right? And the fluid particles whenever these are going just above the fluid, the topmost fluid having the maximum